During this talk, I will present a paper about reduction strategies in Lambda-Calculus, which I co-authored with Małgorzata Biernacka, Witold Haratonik, and my name is Tomasz Drab. The reduction strategies are themselves the object of our study, and the results of this study are summarized in this figure that depicts the relations between them and some of their properties. To make it easier to read, we will consistently refer to every strategy dwelling in our zoo with a picture. Usually, we observe the strategies as an evaluation order, and for example, call by name substitutes the arguments unevaluated and possibly evaluates them later, while call by value evaluates them first and then substitutes them in the formula. The evaluation order may affect the number of reduction steps and even determine if the computation terminates. Therefore, we want to explore their space and compare between them. One notable omission is the call by need strategy that, due to its more complex behavior, still remains in the wild. The plan of this talk corresponds to sections of the paper, and so, in Chapter 2, we will formalize the idea of strategy and related notions. Then, in Chapter 3, we will be able to enjoy the trip to the zoo meaningfully, and in Chapter 4, we will see a new semantic format that concisely describes strategies and helps to reason about them. Chapter 2. As the title of our paper states, we restrict ourselves to pure Lambda-Calculus, whose syntax is given by the following grammar, that in turn can be directly expressed in Coq as an inductive type. There are also families of lambda terms that are ubiquitous in our study. The most important one is the family of normal terms that are already irreducible. Their grammar, using an auxiliary family of neutral terms, ensures that they contain no applications of abstractions. Weak normal terms are expressed with nearly isomorphic grammar. The only difference is that the bodies of abstractions don't have to be normal, because weak reduction does not reduce under lambdas. Similarly, we can define head normal forms and weak head normal forms. We can naturally observe set theoretic inclusions between them. Instead of introducing an inductive type for each family, we formalize them as sets of terms, so the inclusions can be expressed directly. We formalize sets as predicates, as in the standard library in the module ensembles. It is straightforward to define many simple set-theoretic notions this way. We also introduce convenient notations for them, including inclusion, equality of sets, empty set, the full set, and many others. Having that, we can define these predicates by mutual recursion. And then it's easy to prove lemmas that reflect the grammars defining these families. We can also, for example, show that neutral terms are exactly rigid normal terms, or all the inclusions between the families that we've seen on the previous slide. Now, let's try to precisely describe a strategy. As a running example, we take left to right open call by value, and let's see how it works. If there is more than one position where the reduction can take place, this strategy takes the leftmost one. Since it is called by value, it evaluates arguments before they get substituted. And since it's an open variant, it treats as values not only abstractions, but all weak normal terms. Perhaps the most natural way for a programmer to define a strategy is to write a program that performs it. A reducer for left-to-right open call by value can be found in Paulson's textbook. Here we translate it to Coq syntax, having the substitution as a parameter. Evaluation of an application starts with evaluation of left-hand side, then of right-hand side, which is substituted to the left-hand side if it is evaluated to an abstraction. The reduction is weak, so variables and abstractions are already normal forms of this strategy. The definition is clear, and deterministic order of reductions follows from the evaluation order of the meta-language. However, Coq cannot accept this definition because of non-structural recursive call that can cause non-termination. Such evaluators can be intuitively translated into big-step operational semantics format, where we define a relation connecting terms with the normal forms. Again, variables and abstractions are already normal forms. If the left-hand side of an application evaluates to an abstraction, evaluated right-hand side is substituted for its parameter. Otherwise, evaluation of right-hand sides ends the reduction. This definition comes from Sestoff's survey of reduction strategies that strongly inspired our paper. The inductive definition can be formulated in Coq. However, due to presentation of inference rules with multiple independent premises, the evaluation order happens to be only conventional, and we need more specific format to impose left-to-right order. In small-step operational semantics, the relation defines only one reduction step. Note that the rule responsible for substitution restricts it in such a way that the argument has to be in weak normal form already. This imposes the open call-by-value aspect of the strategy. The other two rules allow us to evaluate the function and the argument first. Note that in order to reduce right-hand side, left-hand side has to be already a weak normal term, and this imposes the left-to-right aspect of the strategy. Now we can observe that the role of the last two rules is different, and we can split the definition into two parts. The beta rule, responsible for the substitution, forms a separate relation called a beta contraction. Here it is a beta W contraction because it restricts the argument to be a W that is a weak normal form. The remaining two rules are expressed as a contextual closure of the contraction. This way we obtain the small-step reduction semantics that coincides with left-to-right variant of Accatoli and Guerrieri's open call-by-value. We provide reduction semantics for each strategy in our zoo, and therefore we need to formalize the notion of contexts. Contexts are terms with exactly one occurrence of a special variable called whole that can be used to point to a particular position in a term. Contexts conform to the following grammar, so they can be expressed with an inductive type. We exploit their linear structure and define contexts as lists of elementary contexts called frames. It is the second inductive Coq definition of the two in the whole paper. It is straightforward to define the plug function that puts a subterm back in the whole of its contexts. Having that, we can define families of contexts as we've defined families of terms. We define the set of left-to-right open call-by-value frames as follows. Terms of left frames have to be in weak normal form, while terms of right frames can be any. Left-to-right open call-by-value contexts are lists of such frames in any order. Analogously, we introduce constructors of families that allow us to verify the grammas of context families as lemmas. Moreover, we can show, for example, that open call-by-value contexts are weak contexts, or that call-by-name contexts are exactly weak head contexts. In order to point to some place in a term, we can give a decomposition of this term into a pointed subterm and its contexts. Finally, we can define a strategy as a set of positions in a term where the reduction can take place. The recomposition function is just the uncarried plug function. Now we can simply define sets of normal forms of a given strategy. A term T is a normal form of strategy S if there is no decomposition of T that is accepted by the strategy S. With definition of the quantifier exists at most one, we can also define that a strategy S is deterministic if for any term T there exists at most one decomposition of T that is accepted by the strategy S. The last ingredient to define our strategies is to check if the subterm pointed by the reduction context is indeed contractible, that is indeed an application of an abstraction. To this end, we define families of contractible expressions. This way, we can define a reduction that can perform only beta contraction. More interestingly, we can define the call-by-name strategy as beta contraction in call-by-name context. Similarly, we can define left-to-right open call-by-value using beta W contraction. Definitions of other families are also straightforward. Now we can move to the delayed gratification. Chapter 3. We've already seen the definition of left-to-right open call-by-value. By turning the frames around, we obtain the analogous right-to-left variant, and by allowing any weak context, we obtain a non-deterministic open call-by-value strategy. Similarly, we obtain closed call-by-value by replacing weak normal terms with abstractions, in particular replacing beta W contraction with beta lambda contraction. We can also define the weak reduction as beta contraction in any weak context, and full beta reduction as beta contraction in any context. Call by name can be defined with a very simple grammar of reduction context. This strategy can be extended to the head reduction, that in turn can be extended to the normal order strategy. Thanks to the definition of context families as sets, we can naturally formulate and prove inclusions between them. And thanks to the monotonicity of the Cartesian product, we can limit them to inclusions between strategies, giving a natural, while formal, notion of substrategy. By the way, we can observe that the normal order needs two non-terminal symbols in the grammar of reduction context. It means exactly that this context family is non-uniform. There are also two widely known full reducing strategies whose families of reduction contexts are uniform. They are leftmost innermost and the rightmost innermost. The n beta n contraction makes sure that the contracted function and argument are both already in normal forms. There is also a very small reduction strategy that can be proven to be an intersection of call by name and right to left closed call by value. Interestingly, it is sufficient to reduce closed terms of Del Lago and Akatolis' deterministic Lambda-Calculus, in which they provided simulation of Turing machines. This means that all of its numerous super strategies are also Turing complete. Some properties of the strategies are easy to prove. For example, to decide uniformity, it is enough to give an appropriate set of frames, or to give a reduction context that can be spoiled by reordering its frames as a counterexample. Similarly, it is easy to provide two decompositions of the same term for a non-deterministic strategy. However, proving the determinism of more complex strategies didn't come easy. So we've turned to a new semantic format that provides a more systematic approach to this task. Chapter 4. The first of the two ingredients of phased semantics is the binary operation of strategy sequencing. The sequenced strategies are called phases. An obtained strategy can do a step of the first phase or of the second phase, but given that the term is already in normal form of the first phase. Maybe as expected, strategy sequencing forms a monoid with the empty strategy as the neutral element. The second ingredient are unary operations that can send a strategy of one frame below. For example, so-called left strategy can only peel one right application frame and proceed with the given strategy. Similarly, so-called left abstraction strategy ensures that the term of the peeled right frame is an abstraction. Analogously, we can define right strategies and down strategies that go under lambdas. With the strategy performing only the beta contraction, we can define a phased form of call by name. We use also two other contractions for definitions of other strategies. Now let's see some examples. Call by name can be reflected in phased strategy in two simple ways. The simple representation is also a property of open call by value in left to right version and also in right to left version. If we replace sequencing with union of the strategies, we obtain non-deterministic open call by value. We can also replace the second sequencing with union, then we obtain weak strategy. And if we extend this weak strategy with down strategy that allows to go under lambda, we obtain full beta reduction. In order to represent closed call by value as a phased strategy, we have to introduce some restrictions. And this is also the case in superdeterministic strategy. Quite simple representation is also a property of leftmost innermost and rightmost innermost strategies. They resemble the definition of call by value strategies, and this can explain why they are sometimes confused with call by value strategies, while having different properties because they cannot use fixed point operators because they normalize them before they are applied. We can argue that reasoning about phased strategies is quite simple thanks to their properties. For example, normal forms of sequence strategy are normal forms of both phases. We can also prove that if the left phase is weak, it commutes with beta contraction. And all the unary operations that we've introduced are distributive over sequencing. Now let's move to what phased strategies gave us. Call by name is a well-known strategy that reduces terms to weak head normal form. We've discovered another strategy and prove that it also has this property. It can be also presented in a phased form that helps us to understand how it works. We have seen that left phase of a weak strategy commutes with beta phase. But if we commute the beta phase with right phase of left to right open call by value, we obtain a new strategy in which we can also commute beta phase with its left phase, and then it resembles normal order strategy. But it's a weak strategy, and it's a complete weakly reducing strategy. With phased semantics, it is also easy to extend open call by value to a strong strategy. We can extend left to right open call by value by extra phase of left to right normalization, which is strong. We can also extend left to right open call by value with right to left strong phase, and the same two variants can be done with right to left open call by value. We can also take non-deterministic open call by value and extend it non-deterministically, and this way we obtain a non-deterministic strategy that is a super strategy of the four above, and we call it a non-deterministic strong call by value strategy. Using notions of phased strategies, we can also concisely express what we mean by a conservative extension of a strategy even in the non-deterministic case. Moreover, phased strategies allow us to reason algebraically about strategies. Let's see an example. We can unfold the definition of open call by value and then use the commutativity of beta phase with left phase of weak strategy. then by distributivity we can merge two left phases and optimize the weak strategy that is conservatively extended by the strong strategy. This form of the strategy corresponds to an optimization in implementation of an abstract machine for this strategy. We have also studied a head-reducing strategy that was implemented by Paulson and listed by Sestoft that can be simply obtained by swapping the beta phase with left phase that is not weak. And this head-reducing strategy can be also extended to full reducing strategy that is as complete as normal order strategy. Phased semantics gave us also a standard way to prove what are the shapes of normal forms of the phased strategies, so we could group strategies by the normal forms they form. And these are strategies reducing to weak head normal forms, weak normal forms, head normal forms, and full normal forms. We have also proved about all the deterministic strategies in our zoo that they are indeed deterministic. Thank you for your attention, and I'm curious of your comments and questions.